And we're back. Okay, so let's talk about where we are heading. It might be a good or bad thing. This might be welcome news for some of you that we are not learning anything new. Yay! In either section 4.5 or 4.6.
Oh my God!
Right, so basically what we're going to do now is cut away all of the excess stuff and focus on graphing. Which is why some of you guys might not like that we're not learning anything new. Because what we are going to do now is talk strictly about just graphing. And really, this is like a culmination of a lot of what you've been learning since Algebra 1 in terms of graphing. We're going to go way back, and we're basically going to talk about everything that we could possibly use to create the best graph that we could by hand. And these two sections, section 4.5 and 4.6, are going to be exact opposites of one another. In section 4.5, we are strictly going to graph by hand. I'll allow you to use the red calculator, but no graphing devices at all. Then section 4.6, I actually insist that we're going to spend the whole day talking through Desmos and how Desmos actually allows you to graph not only the original function, but also the derivative and also the second derivative. And we're going to be looking at how all three of those graphs relate to one another. Right? So while section 4.5 is all about graphing by hand, section 4.6 will be graphing with technology and using technology. And like for the quiz, there's a quiz over just sections 4.5 and 4.6. The quiz is going to be in two parts. There's going to be two graphing problems, and then there's going to be one problem where I ask you to graph it all on Desmos. I'll have you construct like a Word document with screenshots of your graphs, and I'll ask you to explain the graphs using and highlighting different parts of the graph and talking about how they relate to one another. Okay, so that's sections 4.5 and 4.6. Nothing new. We're not learning anything new for sections 4.5 and 4.6. The next new thing that's going to come is section 4.7. Okay, so let's get to it then. Now, just showing you the first example that we're going to do. It says use the guidelines to sketch. That's the direction in the homework as well. Use the guidelines to sketch. So what are the guidelines? Well, that's what we're going to be looking at first. Okay. Now, I would insist that you write these down because I'm going to expect that I'm not going to have these provided for you. I'm basically going to say the exact same thing. Use the guidelines. And I'll give you space to do everything. All right, so these are the things. This is basically like everything, starting back way, way, way back in Algebra 1. Everything that we have learned to be able to graph something. The first thing that we talked about way back in Algebra 1 is the domain. The domain is actually very important. We didn't understand the importance of it way back in Algebra 1. But the domain is very important to the look of the graph. The domain. It's often useful to start by determining the domain of the function. That is the set of values of x for which the function is defined. So tell me the domain. More specifically, tell me what parts of the domain, tell me what parts are not in the domain. Like x cannot equal this. X has got to be greater than 0, right? Part 2. B there, intercepts. Find all intercepts. That includes x-intercept and y-intercepts. Now, they put this little piece in here that says, you can omit this step if the equation is too difficult. It's like, no, we can't omit that step. No, we're not going to be omitting that step. It's like, if it's too difficult, just forget about it. Now, the equations that I give you, you should be able to find the x-intercepts. Now, the y-intercept should be super easy. Just plug in 0 for x and see what you get. That's your y-intercept. Finding the x-intercepts, that may be a little bit more difficult. You basically set the equation equal to 0 and then solve for x. But we've been doing that since Algebra 1, right? All right, now, then we move into symmetry, which you may have talked about in Algebra 2. No, probably not in Algebra 2, but definitely in pre-calculus. If something is an odd or even symmetry. Even or odd symmetry. Remember that even symmetry, we definitely covered it here. Even symmetry is that if you plugged in a negative x, it would come out as the exact same function. F of negative x is the same thing as f of x. That is even. Now, what does it mean graphically? Like, how does that help us take a look at our graph? Well, remember that an even function is reflected across the y-axis. If it's an odd function, well, if you plug in negative x, you're going to get negative of the entire function. Basically, you can factor out a negative from the function, and then it should look the same. Where a negative is sitting in front, all the way in front of the function. If that's the case, then it would be odd. And what does it look like if it's odd? Well, then it's a rotation 180 degrees about the origin. Think x cubed. X cubed is a really good example of an odd function, where the right arm is up in the first quadrant and the left arm is down in the third quadrant. And then, these are more algebraic, right? Even and odd functions are algebraic. Plug in negative x and see what happens. But there could be some that are periodic. Now, they say the algebraic definition of something being periodic is the fact that if you have f of x plus p, and you have that plus p in there, even if you add a period, then it would still be f of x. Okay, that it would still be f of x. Even if you added on a full length, then it would still be equivalent to f of x. Now, for our purposes here, the only periodic functions that we're going to be working with are trigonometric ones. That's pretty much it. Here's just another example of a periodic one. And then we have asymptotes. Asymptotes. Did I scroll too fast? Oh, I'm so sorry. Is that good?
Yeah.
Can I go here? Okay.
Don't let them bully you into that.
That's okay. Hey, I'm here for the suits. Yeah.
Just let them bully you. You're here for the money.
That's why I got into teaching.
Makes so much money.
To make sense.
Loads.
That's right.
We got him with the fake piece of gum.
I want to get there.
Okay.
An airplane.
Dude, he got us. Little losers.
How is this possible?
Scammer.
Scammed.
Boys don't They're just advanced in age.
No.
The whole class is listening.
I was gonna tell you. I had a really funny joke.
Guys.
Oh, what did the? Okay, I gotta make sure I say this right. Oh, what did the cannibal get when he showed up late to the potluck?
Which cold shoulder?
The cold shoulder. Did I say that one before?
No, you didn't. You did in stats.
Ah.
What's a duck's favorite part of the body?
The quack. Is this one appropriate for school?
I'm gonna say the butt crack.
The butt quack.
That was inappropriate.
Oh, it is.
All right, we good now?
I'm reporting
Okay.
to the faculty.
I am the faculty.
And then we have asymptotes. We have studied a lot about asymptotes, right? Way back in Algebra 2, we had said, especially with rational functions, that was one of the first times we had horizontal asymptotes. It was rational functions. Remember, if it's top heavy, then there is no asymptote. If it's bottom heavy, then the asymptote is at 0. If it's equal, then the asymptote would be the division of the leading coefficients. But there are some times when we have vertical asymptotes as well. If you've got a rational function and where the denominator equals 0 is usually a vertical asymptote, unless it is factored out and then it become a whole. There are other times that you have vertical asymptotes, like you've got logarithmic functions that have vertical asymptotes. You've got exponential functions that have horizontal asymptotes. But we have basically what we have learned, though, is that if it's a horizontal asymptote, you know this to be true. That as the limit as x goes to positive or negative infinity, but I'll just say positive for right now, of the function is going to be equal to some number c, right? That's what we can say. Now that we've learned limit notation, we can say the limit as x goes to infinity or negative infinity is going to converge to some number c. So if we've got a or if we've got a horizontal asymptote at -3, well then on the right side it's going to level off to -3 as x goes to positive infinity. If I say as x goes to negative infinity, well then on the left side it's going to level off to something. A vertical asymptote, we can kind of switch that around. We say the limit as x approaches some number a, some value of the function is going to be equal to either positive or negative infinity, which basically means that as I get closer and closer to something, it will just continue to increase or decrease, whether it goes positive or negative at that point. But again, rational functions, usually those a values are where the function is undefined, where the denominator is equal to 0. Now, that is probably what you've covered from pre-calc and before, right? You probably knew all that before you stepped into this class. The next slide is the things that we have learned this year and the things that last test had focused on, right? So that's where it's going to be, that's where we're bringing everything together. Last test, we focused on these next parts, E, F, and G. Maybe H, I don't know. E, F, G, H, yeah. Last test, we focused on certain parts, and now we're going to bring everything together. So what are these new parts? Well, intervals of increase and decrease. Doing the increase-decrease test. Okay? We're going to be doing the increase-decrease test. You're going to find your critical values using f prime. So we didn't know how to do that until we learned how to take a derivative. Find the intervals of increase-decrease. Use the ID test. Compute f prime. And find the intervals on which f prime is positive, which means the function is increasing, and when f prime is negative, which means the function is decreasing. Which would then tell you the next part, f, local maximums and minimums. And at that point, once you use the increase-decrease test, those should be pretty simple. If it's going up, then down, then it's a local maximum. If it's going down, then up, it's a local minimum. Although it's usually preferable to use the first derivative test, you can use the second derivative test if the second derivative is easy to find. However, with these things, we're already going to be doing the increase-decrease test. So it would just be like checking your work to do the second derivative test if you would like to. But remember what it is. The second derivative test says if you plug a c value, a critical point, into the second derivative and it comes out negative, that means it's concave downward, means it's the maximum point. If you plug in a critical value into the second derivative and it comes out positive, that means it's a happy face, that means that's a local minimum. If you plug in a c value, critical point, into the second derivative and it comes out at 0, then there is no maximum or minimum at that location. You'll have to find the second derivative anyway because part G says find the concavity. When is it concave up? When is it concave down? And then also that will tell you what the inflection points are as well. And then lastly, put it all together. Sketch the curve. To the best of your ability, sketch the curve. Using the information on items A to G, draw the graph, sketch the asymptotes as dashed lines, plot the intercepts, maximum, minimum, inflection points. Then make the curve pass through those points, rising and falling according to E, according to the intervals of increase and decrease, with concavity and approaching the asymptotes.
How is that a guideline? It's just like telling you what
Just graph.
Yeah.
So that's what I'll be asking you to do for these problems in the homework. Okay, just basically graph the functions. More graphing. So what I would like to do today is get hopefully 2 graphing problems done. Maybe we'll see, maybe 1.5. Might not be able to get through the second one. And then on Monday, I just have to talk about slant asymptotes. And then we'll be good to go. Yeah. If I remember, well, let me check.
It's 80 graphs.
80. This is the next problem that we're going to do if you want to write this down.
Should I have a bunch of room? Library, do I need a library?
8 problems. And we do one of them in class.
We need to find all this guy.
But a couple of them are slant asymptotes.
Yeah, I do like the fish guys.
It's a Nike bag.
No,
Yes, it is.
nobody likes to touch
I haven't seen him in gray.
Are we ready?
We're ready.
We've been ready.
Okay, here we go. Use the guidelines to sketch the curve. Let's get to it then. All right. Let's find the domain. What is the domain of this thing? More importantly, where is this thing undefined? What's not in the domain? Where the denominator is 0. So that means the domain is all x values such that x is not equal to what? Plus or minus 1. If you want to use interval notation, more power to you. But I'm okay if we just say, well, x, it's everywhere, but not -1 or +1. Okay, part B says, then find the intercepts. Now finding, again, the y-intercept is super easy. Just plug in 0 for x. Okay. So here's my y-intercept. Okay, so that would be 2 times 0 squared over 0 squared minus 1. So 0 over -1, so 0. My y-intercept is 0, 0. Now, to find the x-intercept of a rational function, you just set the numerator equal to 0. But in this case, when I do that, I get 2x squared equals 0, x equals 0 again. So my x-intercept is actually the same thing as my y-intercept. Let's just run to the origin point. Part C says to find this symmetry if there is any. So let's plug in -x. That's going to be 2 times -x squared over -x squared minus 1. Well, what's nice about this one is that they're both squared, aren't they? What happens to my negatives? They go away. So 2x squared over x squared minus 1. So what does that tell me? It's even. Even. This tells me that f of x is equivalent to f of -x, which means that this is an even function. Now, how does that help us with the graphing portion? Well, we now know that everything on the right side has to match the left side. This should be symmetrical about the y-axis. So if we know what the right side looks like, we know what the left side looks like. Part D here is the asymptotes. Now, are there going to be asymptotes with this type of function? Yeah, because it is a rational function. So we know that there are asymptotes. If it was a polynomial, would there be asymptotes? No. If it was a trigonometric, are there going to be asymptotes? Depends. Is it tangent? If it's sine or cosine, then the answer is no. But if it's tangent, the answer is yes. All right, so let's take a look here. Let's do vertical asymptotes first. Now, the vertical asymptotes are where the denominator is equal to 0, right? But we also should be careful the denominator is equal to 0 and the fact that you got to be careful of if anything could cancel out. Because if it's canceling out, it's no longer an asymptote but a hole. But in this case, nothing's going to cancel top to bottom. So I just set x squared minus 1 equal to 0. So x is equal to plus or minus 1 again. So my vertical asymptotes are at x equals 1 and x equals -1. I actually have 2 vertical asymptotes. Where's my horizontal asymptote? What's that? 2. Where'd that come from? Yeah. Look at the degree on the top and the bottom. They're both x squared, right? They're both x squared. So that means this is the same on top and bottom. So I take the leading coefficient off the top divided by the leading coefficient off the bottom. 2 over 1 is 2. Okay, so I've got 2 vertical asymptotes, a horizontal asymptote at y equals 2. All right, part E says, now let's do all the calculus. Let's start with the increase-decrease test. I'm going to write this over here so I have it. 2x squared over x squared minus 1. Okay, so let's find the derivative. Let's find the derivative. Be careful, I got to use quotient rule here, right? So low, f prime of x is equal to low, which is x squared minus 1, d high, which is 4x, minus high, derivative of low, all divided by low squared. Remember when that was like a big deal in and of itself? Just doing a quotient rule problem. Whoa, that was a lot.
We're growing so much.
You gave us a big book on this.
4x cubed minus 4x. This is a minus 4x cubed. Those are ditto marks. So that means we've got a negative 4x all over x squared minus 1 squared. Okay, so there's my derivative. Where are my critical values now? Where are my critical points? 0. Good. 0, 1, and negative 1. We see the 0 coming from the numerator, setting negative 4x equal to 0. And the plus or minus 1 is where the derivative would be undefined, where the denominator equals 0. And that's that plus or minus 1. Okay, so now we do a quick number line test. Yeah, we're only at D.
This is C.
No, I'm talking about like the critical number test.
Oh, yeah. Okay, now, pare down what you're looking for. What do I mean by that? Look at the denominator of the derivative. Look at the denominator. Isn't that always going to be positive? Okay, so when I divide by a positive number, it's just going to stay the same sign as whatever the numerator is, right? So think back. Work smarter, not harder. I don't have to care about the denominator. I really only care about what's happening in my numerator. So like if I plug in negative 4x, if I plug in negative 2 into negative 4x, what is it going to be? Positive or negative? Positive. And a positive is a positive. If I plug in negative 1/2, negative times a negative is a positive, and it's still divided by a positive. So it's positive in there. If I plug in 0.5, positive 0.5, negative divided by positive is a negative. If I plug in 2, negative divided by positive is a negative. See, you don't have to actually run values because you only care about the sign. That'll make things go a little quicker. All right, so now this is going to increase where? Negative infinity to 0. And it's going to be decreasing 0 to infinity. Now, part F is just a direct result. I'll just like tack it on over here. What's happening at 0 then? What's happening at 0? Not inflection.
Maximum.
Yeah, I'm increasing to decreasing, so it is a maximum point. Now, what's the y value at 0? You don't even need to. 0, 0. It was your intercept. If you needed to, you could plug it into the original, but we've already done that. Okay, let's take a look at part G then. Now, G is the concavity test, right? No? Grace is just, no, it's not. No. That is really funny. All right, so we find the second derivative. Low. Oops. D high minus high D low. Now, the derivative of low, chain rule, 2x squared minus 1, and then I would say to the first power, times the derivative of the inside. And that's all divided by x squared minus 1 squared squared. So to the fourth. Yeah.
Are we supposed to remember all these steps?
Yes.
There's really only like.
Luke Candle's foot is on the table.
Now, take a look here. Let's simplify things real quick. What do you notice in each term here?
Oh, buddy.
So this can go away, this can go away, and that power can go down to 3.
That's gone. That's gone.
And to reduce it like that, you need to make sure that that is in each term. It's going to be. When that happens like that, it's going to be, especially when doing f double prime. So on the left side, that gives me a negative 4x squared plus 4 when I distribute the negative 4 in. Here, those double negatives will turn positive, and that's going to be a 4 times 2 times 2, 16. X times x is x squared. All divided by x squared minus 1 cubed.
Wait, why is it not squared on the side?
Where? Here?
Yeah, because if you take the x squared minus 1 squared, wouldn't it be just taking 2 of them away from the denominator? And then taking another?
No, one of them had to stay.
Why?
One of them just had to stay here because there was only one in each term.
Oh, okay.
Yeah.
Singular.
Now, reduce the top. 12x squared plus 4 over x squared minus 1 cubed. So there's f double prime. The critical points of that are where the inflection points could be. Now, let's go for the zeros first. We say 12x squared plus 4 equals 0. Well, that's going to be something not good. There's no solution there. But I still at the bottom, right? Because it's not only the zeros, but also where the second derivative does not exist. X squared minus 1 cubed is equal to 0. So x squared minus 1 is equal to 0. So x is equal to that plus or minus 1 again. So when I run my concavity test, I got to use positive and negative 1. Now, again, work smarter. For the second derivative, look at the numerator now. Isn't the numerator going to stay positive? Yeah, now the numerator is going to stay positive. So I really only care about what's happening in the denominator now. So if I plug in negative 2, That's going to give me 4 minus 1, positive 3. Cubed is 3, or cubed is positive. If I plug in something in between negative 1 and 1, say 0. 0 minus 1 is negative 1. Cubed is negative. They're being mean. They're being mean to you.
What happened? A disruption in the class? Oh, is she out?
Hey.
We're lacking. Looks like we got to step up our disruption.
And then 2 is going to be the same thing as negative 2. That's going to turn out positive as well, right? Yeah, sometimes you need to. You know what's funny? I was rewatching this video from last year just to like jog my memory on how to teach it, and I roasted somebody because they were falling asleep. Must just be this lesson, you know. Must just be me. It's like a podcast. It's like, yeah, you just try to. You know, I think I said in the video, I was like, I think you needed to.
And you
just-
didn't even bill.
Yeah, him and Popio. Who else was back there? It was Thomas and Carter Blankenship
Oh, did you have this class? Did you have them fourth period?
last year. Yeah, 4th period last year.
You probably heard me out in the hall then, because I sat out there a lot.
Oh, really?
Did you ever hear like a hive screeching, like a?
No, I don't know.
Because I remember one of the times you closed the door because we were being loud.
So this is concave up from negative infinity to negative 1, and then as well from 1 to infinity. This is concave down from negative 1 to 1.
Possible stupid question, but whenever you were testing on the second one, you plugged that into the double prime equation, right?
Yeah. Now, where are the inflection points? Good. Yeah, this is almost like a trick question here. Because you would be tempted to say negative 1 and positive 1, right? Are they in the domain? No. See, now this, what's happening in negative 1 and positive 1? What's happening in negative 1 and positive 1?
They're not there.
There are asymptotes there. So they're not inflections, but they are asymptotes. There are no inflection points.
So how's the concavity change and not being an inflection point?
They just go to.
Let's look. Let's graph it now.
Concavity.
Concave.
Please don't.
If that's a criminal tooth infection is a concavity.
Concave. Criminal tooth infection. Wow.
That's a good one. That's original.
Up top.
What
Oh,
time?
that
Did,
was weak.
what time did the age village end this?
All right. So let's first start off by graphing the
Sick. Oh, for real? What did you find?
Current time in Asia.
current time in Asia.
Too many cons.
So there are the asymptotes, right? Where is the? Because I'm going from the top down. Where is the x-intercept and y-intercept? 0, 0, which is also what? What else is 0, 0?
The max.
The max. So it must act like this. Is it, did I draw it correctly? Is it concave downward from negative 1 to 1?
Mhm.
Yeah. Okay, so let's see what's happening to the right of 1. To the right of 1, should it be concave upward or concave downward? Concave upward. See, I really kind of have two options. I could draw that because I know it's got to attach to these asymptotes, right? I could either draw it here. Ooh, don't do that. I could either draw it down here or I could draw it up here. If I drew it down here, would that be concave upward? No, that would be concave downward, which means that I should draw it up here. And I don't even need to think about the left side because I know this is even symmetry. Whoa, that was a poor drawing.
What kind of function is that?
Rational.
Louisville Y, 7 o'clock. Be there.
There it is.
There also wasn't any excess.
Good point. Matt also said Matthew. Why did I call you Matt?
Why you do that?
Matthew also said. He said there's also no other x-intercept, so that's another reason why we know that it was not
I'm on the boat.
on the underside of the asymptote.
So are we gonna have like a?
We'll stop there.
It's gonna be fun homework.
I get long-winded though. You guys can tell me
Yeah.
I feel like I can actually do this. Oh yeah, I feel like this is gonna be.
Let me see how many my are left.
Yeah, if we have 8 of those for the homework. Did you stop the video? No.